Hey, hi everyone, this is Vivek and welcome to this second episode of Codeforces Weekly. And in this particular video, we're going to talk about this range and partition problem from CF round 768, which is a div 1, like corresponding div 2 also has this problem. And this particular question is really interesting because out of all the 6 problems that I have solved as of now on the weekly, this is the problem that gave me the most hard time because I think it took me around 20 minutes to kind of fully understand the full proof of it. I mean, like fully kind of justify myself that okay, it's kind of working all together, and then kind of like go into the solution that okay, fine, I can code it up, right? And in this particular problem, this is not really like a very simple one because it's more on the constructive side. But again, like we're gonna go deep into how do you think about these problems and how do you actually structure up the content, right? And how do you kind of thought like how do you build the whole thought process all together for it, right? The solution is not really the main stuff because it's also present in editorials. What I'm going to try is explain you how did I think about kind of coming up to that conclusion, right? Because I think the way it's explained in the editorial is very direct, but again, like how do you think about these things is what is very important, right? So given a array of n numbers and find a range x to y, and split the A into k subarrays such that each subarray is formed by several continuous elements of A. That is, it is equal to, like, there are some subarrays. Each element belongs to only one subarray, and for each subarray, the number of elements in x to y is strictly greater than the number of elements outside the range, right? And element at index I is inside the range if and only if AI is less than, like, it's in the range x to y. We have to print any solution that minimizes y minus x. So we have to find the smallest like kind of range x to y such that we can split it in exactly k subarrays such that in every window the number of elements in every subarray, the case subarray that we have split it into, the number of elements in the window is strictly greater than the number of elements outside the range, right? Cool. So let's try to think about this particular problem. This is what is there. The ranges are 10 to the power 5. I mean, we have to do something linearish of n log-ish kind of thing over here. Most probably values are up to n. That's interesting. The values are up till n only. LIRI is up to n as well. And we have some sample. I think I've got the problem, so it's not really that difficult. But again, this is a constructive kind of a problem, but it's a very nice thought process. So this is the reading part where you understand all of these things. Next we move into, let's say, thinking about the observations and kind of building the solution. Also in this observation and like building phase, whatever things that you learned right now, like kind of jot them down with while you're getting through it, or you're kind of striking you that okay, this is something which is very interesting, maybe I should keep this in mind. So this is how you improve in CP, right? You kind of keep building this repertoire of like good techniques that you have learned, and then eventually you kind of become really good when you have a big list of that, right? So that's obviously one of the like only way I think, but again, you need to do that smartly. So this is what we're kind of talking about in this problem. Let's move into the decomposition of this. So we read it, right? The reading phase, I mean, you must be like, if you have seen the previous videos, if you have not, please do check them out after this video. It's kind of independent, but still, like if you have gone through them, you must be like kind of already familiar with what we do in the video format, right? So read, solve, and then formulate or observe basically. First of all, you need to observe, right? So this really weird problem of finding a window, and then you have this array. We have to partition this into, let's put a partition k minus 1 partition, so that let's say k equal to 3. So we put exactly two partitions so that it kind of becomes 3 subarrays, and then in each of the subarray we kind of want to find okay, what is the, like in each subarray the number of elements which is in this window has to be greater than the numbers not in that window, strictly greater than that. Okay, so that's there. Let's think about okay, what is the exact condition for which we kind of how do we evaluate this kind of a condition, right? That there is this random window where we have to kind of make sure that there is a solution, right? So there is this too much of variabilities there. X can change, y can change, the way you partition with k is changing, everything is changing, right? So we need to have a pivot point wherein like what do we iterate or what do we find, and what can we find as a consequence of that. Okay, this is a very common flow of problems that we solve, that out of so many variables that can be changed, that is up to you to decide on optimally how do you do that. What is the thing that you kind of iterate on, or you kind of like search on, and what are the things that you can follow up according to that, right? So if you think about the three things, number one, the X and Y choices, and then the way you partition, right? The way you partition. Now it's very, very obvious that the way of choices of like the way you choose XY determines the partition, right? It's not the other way around, because if you partition first, for every partition you're going to get a range of X and Y's, and it's going to be very, very confusing, right? So partitioning is very, very like generic thing, and even the number of partition can be very large, so we cannot really iterate on partition. So first of all, we understand that okay, this is something that we are searching correctly, and then accordingly according to the values X and Y's, we're going to be partitioning it, right? So this is the natural flow on how do you go, what are the things that I need to, that are in my control to tweak, and what I can optimize on, and then think about the dependency that is there among them. So we have X and Y, which kind of creates a dependent, which has partition depending upon it, right? So we think about okay, how do we optimize X and Y? Forget about partition, right? We have to find a partition, but how do we find an optimal X and Y? So we need to find a such like possible X and Y. So there is one more condition given to us, that Y minus X needs to be minimized, right? So whenever there is this condition, right, that the subarray length needs to be minimum, or the range needs to be minimum or maximum maybe as well, there are different kind of possibilities that generate, right? If we now go back to that listing of kind of techniques, brute force is obviously not an option because all pairs cannot be checked, and n square is not feasible in this problem. Greedy might be possible, right? There is some random greedy observation which kind of gives us the X and Y values, maybe. Maths, not really, because values are pretty random, so maths doesn't really seem to be the correct way. Binary search is possible, right? And then DP might be possible because partitioning is there, but the number of variables are too high. It's like n, so n is up to 10 to the power 5. So even if we keep one more information, it's gonna become 10 to the power 10, which is not possible. So we need to solve it in linear DP. That is also 1D DP, right? Can we do it in 1D DP with some extra 1 or 2 information? Seems to be difficult, but let's keep it an option. Graph doesn't seem to be anyway. So these are the three options that we have altogether, right? Only options that we have. Now we have greedy, binary search, and DP in option. And I feel DP is not going to be there because the number of ways in which you can kind of model things or like restrict things is pretty like open in this problem, right? The X is changing, Y is changing, partitioning is changing, and restricting it in just 1D DP with just few parameters is very difficult. Maybe this partitioning is something that can be found out using DP. So that is a sub problem, but again, DP is not a correct way to go about it, right? Now greedy and binary search is left, right? So my personal rule that I follow in general for solving such questions where there can be a possibility of constructive ideas or greedy is I explore greedy at the end, okay? Because other things, if are there, are possible, then they are for sure correct. Greedy is something which comes up constructively and might not be correct at times, right? So I personally explore greedy at the end. You can use anything that you want, but let's explore greedy at the end. Let's think about binary search, right? That we need to minimize this. So let's binary search on the answer. That's a very, very standard style, binary search on answer, right? So if we know the window length, what can we do? So now it's like if you know the value of X, you can find out the value of Y and so on. Like you can easily do that because the window length is fixed if you're doing binary search and all. But let's think about this problem a bit more. Like let's try to build in more observations about this. So let's say we know the value of X and Y, right? Like, I mean, if we know the value of X, we know the value of Y. If we are sort of doing some binary search, because this binary search is going to give us the length with an extra cost of order log n being multiplied, right? So now that reduces the like kind of restrictions on these three things. I'm not really sure like if every length would be possible, right? So whether the feasibility of binary search is second thing, but let's think about, okay, what is the like possibility, like how do we model this problem if we, so for binary search there is two things, right? One is it needs to be monotone space. Second, it needs to be a possibility that we can use some sort of let's say check function to kind of check whether this value is feasible or not, right? Check function needs to be created, like at this mid, is it feasible or not? How to do that? So that leads to this simple problem that, okay, if you're given the value of X comma Y, how do you partition the array? Okay, how do you partition? Given X comma Y, partition the array. Okay, now again there is this concept of the number of elements in every X comma Y is going to be, number of elements in X comma Y is going to be bigger than the number of elements not in that. So there is this concept of majority element, right? That at least half, more than half should be in the range. So again, any number, let's say x sum a of I, which is in this range, is going to contribute a +1, and then ai not in this, is going to contribute -1, right? So essentially we kind of need to partition, like there is a bunch of +1s, -1s, right? And we need to, let's say, partition it into k equal to p number of ways, right? So if you think about how we are kind of doing it, is like we have this array over here and we need to partition it into 3 partitions such that the let's say the number of +1s is more than number of -1 in each partition, right? Wherein we can say that the sum of each partition is bigger than 0, right? So we can think about like starting from over here, okay? Let's say there is this part where we stop. Let's say we stop over here, okay? Because this is something which is greater than 0, okay? Let's say we start from over here again. This is also greater than 0, right? And then again we start over here, we keep going and we get that over here it's greater than 0. And we can see that actually these 3 things, like if you partition it this way, like every partition satisfies, right? So essentially this partition is greater than 0, this partition is greater than 0, this partition is greater than 0. So we can kind of get a condition that if the whole sum, okay, of the whole array is greater than equal to k, then only it's possible, because like you have to at least increase k times, right? Then only you have 3 partitions, k partitions in general. So if the total sum of the array is greater than equal to k, then it's possible, or else not, right? If it's possible, then think about it. Why is it always possible to partition it? Because it's a gradual increase, right? It's always a +1 or -1. So like from the start with 0, there is, so if you think about the values, it's going to be 0. Like let's say this is the value, and like let's say we are kind of doing a prefix sum kind of thing over here, right? So let's say there is this partition value which kind of increases, and then like maybe after decreasing it ends at k, something like this. So wherever we first time get a 1, we can make a partition over there. Wherever we get the first time 2, we can make a partition. Wherever we get the next, like from over here, the next increase point, okay, maybe over here itself we can get a thing. Next from over here we can get this point 4, next 5, next 6, and so on. Like obviously we don't need to go till this point because we need to stop at k. So we will stop at k, and we can do that. Like when the last partition is there, we can take all of that because it's going to satisfy it altogether, even if it's more than k, right? So it's going to satisfy it there, and we can build it this way. And we can also note that if we merge, if we have more than k partitions, then we can also do it in equal to k partitions, right? Because if you merge 2 partitions, they are never going to dissatisfy the like condition, because like if 2 partitions both have independently more number of elements in the range x to y, even if you combine them, it's going to contain more numbers. Like if you combine the same majority in both of them, it remains majority. Okay, this is something which is true. So this is what we can use in this particular problem, and essentially this is what is going to give us the solution idea for this problem. So note that the simple condition to check where a particular value is present is when the final sum of the array, okay, the number of elements in that array in the range x to y is greater than equal to 0, then it's always possible. Why? Number one, we can use this greedy process to kind of keep generating the numbers. The first time we see a +1, like start with 0 sum, we see a +1, then we kind of say that it's the first subarray. Then whenever we see the next +2, we see that it's a subarray. Then from over there, whenever we see the +3, and we can say the it's the next subarray. We can do this also. Like in at max, we can do 1 partition, 2 partition. Then sorry, it should not be, these partitions would not be valid up till these 3 partitions, right? The max we can do is 3 partitions. We can also do 2 partition. If you want to do 2 partitions, then like this is also 2 partitions. Like if you merge these two, that's still fine, right? So anything greater than equal to k, anything less than equal to k is possible if you can do k, right? So possibility wise, we can kind of do something like that. But how do we find this x and y? So we find this very neat condition that if the final sum of elements in the range x to y is greater than equal to k, then we are done. And now we can actually use binary search in very, very neat way to find the possibility for thing. So now there are 2 parts to it, right? Number 1, find like sum x to y, okay? Number 2, generate solution, right? I mean, I'm kind of merging the formulate step into this itself, because I mean I think it's not very like separate properly. Generate, but again it's fine. generate for a particular x comma y, right? And this generation is nothing but like you can do some sort of greedy process, or you can keep dividing it using prefix sums if you want to. So like like start from the first, and as soon as you get a subarray with sum greater than 0, just check it, take it as a chunk and make it a particular subarray, then start with the next one. Since the sum is greater than or equal to k, you're going to get the solution for sure, okay, if it's possible. And find some x comma y is what we can do using simply, like obviously there is going to be always a solution, because if you take the full subarray, I mean 1 to n, everything is majority, so you're done with the problem, right? So this is there. Find some x to y. So what we can do is we need to just find this very effectively. So the number of condition is that for a particular x comma y, number of elements in the whole array in the range x to y has to be greater than or equal to k. That's the only condition that needs to be there. If it is there, it is possible, and the way to generate is something that we have talked about. So now we need to find some x comma y with that, with minimum x y minus x, and we can do multiple different things for this process. I think one very neat way is maybe like to loop over x, like loop on x, and then maybe binary search y, like what kind of y is there, binary search the value of y, and then we know that every element is in the range 1 to n, so we can maintain the frequency count and build a prefix sum on that. So maybe like if let's say 1 0 1 2 3 4 5 6 is there, so we can build 1 1 3 1, something like this, 0 0 0, and then maybe we can build a prefix sum on this array, and then easily we can get this number of elements in a range from x to y in the whole array, right? And we can check this in order 1. So checking this is very much possible in order 1, because we can check any range neatly, because we can build the frequency array and check the whole array at once. And then for it, we just need to find x minus y as minimum, so we can do binary search on the length and then loop over x, like order n over here, and then order log n over here, and then order 1 to search for that. Once we have that, this generate is just a simple order n process, right? So that is pretty much possible. One other way in which we can do this is, let's say we like sort the values a1 a2, which is a very neat way to kind of solve this problem in order n, is that a1 a2 a3 up till an is the sorted values of the array, okay, sorted array. So now we need at least k elements in this, in the, like the whole sum needs to be greater than or equal to k, right? The whole sum needs to be greater than or equal to k. So what we can do is we can kind of see that if we take a1 as the x, right, anyways the interesting points are just these values that are there in the array. If a1 is the starting point, what is the value that we should take so that the majority elements remain there? So what we can do is from a1 we can take at least like k number of like k extra elements into the whole part. So the way we can decompose this is like there should be k different majority elements. So the number of plus ones, so let's say if this is x, there is going to be some y. So these are the elements that are going to give us the plus ones, and these are the things that are going to give us minus 1. And in total, this sum is going to be equal to what we can say is greater than equal to k, right? So what we can say is y minus x plus 1, like this length, okay, so this is going to contribute a plus 1 minus n minus this all stuff, right? I'm just going to replace this x minus y plus 1 with a length right now, just to keep it simple. Has to be greater than or equal to k, right? This multiplied by minus 1. I mean, it's already multiplied, so I have taken a minus over here already. So this contributes plus 1, minus 1 multiplied by this length has to be greater than or equal to k. And from there, we can get the value of, let's say, the length itself. So it's going to be equal to, so this is 2 length is greater than or equal to k, and length is going to be greater than, sorry, n plus k, and length is greater than or equal to n plus k by 2, right? And we can kind of seal this off to make it proper division, right? Because we don't want to have floating point values. And from over here we can see that fine, like this gives us the value of y minus x plus 1, right? And if we take this plus 1 to this side, y is equal to x plus 1 subtracted from a floor division is going to be n plus k minus 1, n plus k minus 1 by 2, right? So this is there, and this is going to be the value of y for a corresponding x. So for every x, like in the sorted array, you can get the value y very easily, and then you can check that up, right? So for this is the value x, this is the value y that it's gonna be, like whatever index, like a of this index, I mean to say, right? That's going to be the final value, and accordingly you can check if it is, like, it's going to be feasible. So the best length that is there, like the best y minus the value x is going to be there. This is, I think I should write position of x, but anyways, I think you got the point, right? That whatever position x is present, or like how much do I need to move forward is this. So correspondingly find that element, the difference between them, like just go through all the windows, and then whatever is the optimal, just take that and generate the solution. This can solve. So since we know this length is fixed, like we can simply do like order n number of such stuff, and this is going to be order n, right? And in order n we get the best length, like whatever aj minus ai is the optimal. This is going to be the value y minus x, right? And this is going to be the, and then whatever this comes out, we can simply use this to generate the thing in order and in a greedy kind of a process as well, right? That is pretty much possible. So in total you can also solve this problem in order and using this observation. But again, I think the main idea that was there that I wanted to talk about is how do you go about thinking about these problems, because like on the first glance this might be a very constructive problem and can be difficult, right? So this is how you think about it, that okay, like what are the parameters I can tweak, which one to tweak first, which one is the main like changing one, how do I get the other one if I know the first one, and so on. So this is how you do exploration in ad hoc problems, right? Maybe we're gonna talk about these things in a separate video altogether, but again, this is something we're gonna like do for this problem, right? And this is again the whole observation. I mean, now we have a solution in order n. So if you go to the simple final formulate step, right, formulate, that's pretty easy. Like if you have understood everything, take the a array, right, and sort it up. So and then from this sorted array we know that any index I combined with I plus n plus k minus 1 by 2 gives us a solution. So whatever this x and y value are over here in these two j indexes, j is equal to these two indexes. So we need to find the minimum value of y minus x altogether, right, from all the different ij's. So we can loop over I, j is fixed, and then get the minimum of all yj's, and then whatever minimum length we get, corresponding x and y's can be used to generate, so we get a final. So from this we get x comma y, and then finally we use that to generate x using a array and then x comma y. Note that you don't use the sorted array, you use the original array, but again that's fine. You generate this and you get the final partitioning, whatever is required in the problem if you have to print this, right? So that's, I guess, there to for this particular problem. This is the final formulate step, and again after this, like, everything is going to be coding and debugging it up if you require that. But I guess this is a very, very interesting problem to think about, and I mean, I would think this is something which is going to be hard for medium level coders even, because the observations are pretty high. I mean, I personally feel that at least for Indian people, observation is something that they get a lot of bottleneck in, rather than like knowing a lot of data structures and algorithms. So this is what I think is there. So again, this is something I will leave for you to code, and I hope the series is something that you are enjoying. If you have not checked out the videos, do check them out. I think they are of good value. I try my best to put out as good content as possible, but feel free to suggest me if you need some like improvements in the things, and I will try to tweak in the video if I find them just right. Also, do let me know if you like would want to talk about few other things in the on the channel. I'm quite open to more options that are there, but again, these three things, like 6 p.m. videos on Tuesdays, Thursdays, and Tuesdays, Thursdays, and Saturdays is gonna be there rolling out as long as you guys want it, right? So that's there. Also, this is, I guess, the end of the second week, so do share it up with people who don't know about this channel, because I personally, I feel I would love to give more time to creating content rather than making sure that, like, okay, YouTube kind of plays around and there are people to watch the videos and all. So I would love to give more time to structuring the content and creating these videos, and I would leave the helping part for you guys, that okay, to build this community in a bit bigger way, and then like letting more people to know about it to you. And what you can do is like kind of share it with your college groups or people where people like learn CP in general, and like they would be able to like kind of get to this content if they want, right? I mean, obviously not everybody is there on YouTube to learn stuff, but if you're watching these videos, I personally feel that you are like already on the correct path. So stay tuned, and we're gonna have more such stuff. Do share it up with people who are interested or might be interested in these things, because I feel these kind of contents do require a good audience, and if somebody gets this at an early stage, they can get a lot of improvement in the whole journey, right? So that's all for this particular video. Thanks for tuning in, and see you in the next week with more such problems, right? So bye bye.